Okay, this is section 12.8, and this blank handout is available on Canvas, so I recommend that you print it out and follow along as you're taking the notes. So we're going to do a quick recap. Let's see what we're trying to even do today. We're now going to extend what we did with polar coordinates yesterday to try to evaluate more complicated double integrals using general coordinate changes. So our last lesson was specific to regions that were great to switch to polar, but now we're going to say, what about if I wanted to switch to a totally different coordinate system, a more general one? So we've actually done this before in Calc 1 when we changed variables for single integrals, and so let's remind ourselves how we do that. Let's look at this basic example, e to the x over 2 dx. Okay, so this is a classic example. Let's actually just sketch for a minute. I'm going to rewrite it here. It's a classic example where I could use a u substitution. I'm just going to sketch my region of integration. So in this case, that's the region 0 to 2. And so this is the region of integration as it is. And then the typical thing we do is we say, okay, let's do a u substitution. So let's go backwards here. Let's let u be x over 2, which means that du is 1/2 dx. And then this whole integral becomes the integral of e to the u. And then my let's solve this here. So you can see that this means that dx is going to be 2 du. So we replace dx with 2 du. And then let's look at my bounds. So my lower bound is going to start, u is x over 2. If x is 0, it's going to start when u is 0. And my upper bound is going to end when u is 1. Okay, so notice this new region of integration when I've done this change of variables. Now I'm integrating in u space, and I'm integrating from 0, but just to 1 now. Okay, so in order for these two integrals to be equivalent, in order for this integral to give me the same answer as when I switch it to u space, I need to take into account the fact that in going from the right to the left, the x to the u, I have shrunk my region of integration, by a factor of 2. Integration. And that's the 2, that factor shows up right here in the integrand. That's how I take into account that I shrunk the region so that I don't change the value of the integral. I get the same thing. And we're going to do this now for double integrals, where my integrand's a function of more than just one variable. And we're also going to need to take into account, if we change the region that we're integrating over, how this will affect, or how we can account for that in the integrand so that we still get the same answer. Okay, so let's see how we can do this with double integrals. In general, we're going to try to use a change of coordinates in double integrals when I have a region that's hard to integrate in Cartesian, or when my integrand is too hard to integrate with my current Cartesian coordinates. So in general, we're just trying to do this to make things easier, just like with the u sub. And the goal is to simplify. Okay, so we call it change of coordinates, or you'll also hear it called a transformation. And so I'm going to give you a very basic example down below here where we can just visualize one basic transformation. And then we'll go to a more general case. Okay, let's say we wanted to do this double integral. And I said, hey, for whatever reason, maybe the way my integrand's set up, I decided it's going to be easier if I make this transformation where I let u be x over 2 and v be y over 3. And now I want to rewrite an equivalent double integral. So if we picture this as like the signed volume of some mountain over a region, I'm going to change the region I integrate over, but I don't want to change the actual volume at the end of the day. So I need to still get the same answer, even though I'm going to change the region just like up above when we shrunk the region by a factor of 2. So first, let's call these, let's start over here, the region of integration in the xy plane. We're just going to call that R, and let's sketch it. X is going from 0 to 2. So here's 2, and y is going from 0 to 3. So it's just this region right here. Okay, and then notice what my new region is going to become with my change of coordinates. My new region, and it might help, so we can solve here. Oops, let's go back to the right. If we solve u equals x over 2, this means x is going to be 2u, and this means y is going to be 3v. Okay, but let's see what our new region is going to look like. So instead of, actually it's easier to see up here, when x is 2, if I plug it in, then u becomes 1. So I can map this right-hand corner right to here. And then when y is 3, v also becomes 1, so I can map my y values. So if we take any given point, I could take any point right in here. I can even take the point 1, 2, and if I go map that, when x is 1, u will be 1/2, and v will be 2/3. So it'll get mapped to like that little point right there. But you notice every little point in my region is going to get mapped to this new square. So I'm going to call this new region, we'll call it G, and let's color it in. Oops. Okay, and so this is in U and V, and this is X and Y. And so notice what's happening, we're calling this G. What's happening to the area of this region. I have now shrunk it by a factor of 6, because the area of the yellow region was 6 and the area of my new region is just 1. And I'd like to now integrate over my new region, so let's see what happens to my bounds. This is telling me u is just going from 0 to 1, and v is just going from 0 to 1. And then my function, f, I'm going to replace x with 2u and y with 3v. But now I need to take into account the fact that I changed the area of the region I'm integrating over, because I don't want to actually change the value of the integral itself. And so because I shrunk down by a factor of 6, I need to say, oh wait, I need to end up putting that back in, just like we did with our u sub up above, so that the area of one little du dv times 6 will get me back to the actual area over here. If here's like a tiny little du dv up in the right-hand corner, then when I multiply it by 6, I'm going to get back to the actual area. So this is how we take into account that we shrunk things down. Okay, so let's look at this in a little bit more of a general situation.